Good evening, ladies and gentlemen. Tonight's talk is about solids, and we're going to be dealing with some structures of some different types of solids, from ionic compound solids, and we'll also be talking a little bit about alloys as well. So let's start right with the structure of solids. As first off with an ionic compound. As we know, an ionic compound is a metal and a nonmetal, and these are typically arranged in a three-dimensional array. So I'll give you an example of potassium chloride here. So if we had potassium chloride, we would have a three-dimensional array of, let's say that's a potassium ion. We can go ahead and make that a little bit bigger. Let's make a potassium ion next to a chloride ion, which would then be next to a potassium ion. And this is in the solid form. And we could keep drawing this with alternating potassium and chlorines and potassium chlorines. And we'll remember this is kind of in a three-dimensional plane, so we can make a cube out of it, little crystals and things like that. Keep going with potassiums and chlorines all the way back and all the way across the top, and that would be our solid potassium chloride. Solid. And if we tried to take an ionic solid, such as potassium chloride we're talking about, it's not necessarily going to conduct electricity, but it will if we melt it. So if we heat it up high enough into its molten state, it can conduct electricity, or we could dissolve it in water. And whenever we dissolve these things in water, that tells us we've got an electrolyte. And scrolling down here, just taking a look at, this is an image from Gatorade bottle. And Gatorade is marketed as having electrolytes, help you replace electrolytes that you lose when you sweat a lot, when you're some physical activity. And the two main electrolytes in Gatorade are salts, and that's sodium chloride, as we know. And we also have potassium dihydrogen phosphate, which Gatorade likes to call monopotassium phosphate, which is just kind of the trade name or a common name for potassium dihydrogen phosphate with that dihydrogen phosphate. So when these are put into solution, we know that they're going to ionize. They're both soluble, and so sodium is going to break up into the sodium ion, and we know that chlorine is going to break up into the chloride ion, just like that. And so now we have these ions floating around solution, and then we're going to form a weak electrolyte. And those weak electrolytes are what you're losing. So you're basically drinking salty, sugary water with a little bit of added flavor to it, which is probably something that's not natural. We also have on the potassium dihydrogen phosphate, you've got that potassium ion, and then of course you have your dihydrogen phosphate ion, which is H2PO41-. And those are our ions that are floating around in Gatorade as well. So they start off as solid. Now let's talk about melting points when it comes to ionic solids, and this is governed by Coulomb's law. And so Coulomb's law is going to be E is equal to, and E is going to be our lattice energy, and that was the energy that was required to take a solid ionic compound and vaporize it, is equal to K, which is just a constant. And then we're going to take Q1 multiplied by Q2, and I'm going to rewrite it over here just so we can see it in a different way. Q1 over Q2 divided by R. Now Q1 and Q2 are going to be our charges. And so the difference in charges between our anion and our cation, and then R is going to be our distance between these two ions. So if, as you should be able to see from this fraction, if we increase the distance between two ions, we are going to decrease the lattice energy. And we talked about this a little bit before. So because we're increasing a denominator, whatever we're working with is going to decrease, like the whatever it's solved for. And the charges, if we were to increase the charge between two atoms, then we would scratch this out and we would increase the lattice energy according to Coulomb's law. So what's the concept behind this? Well, the concept behind this is this also governs melting points on solids. So if we increase the distance between two ions, we're going to decrease the lattice energy. I'm sorry. Yeah, that's right. We're going to decrease the lattice energy, which is going to decrease our melting points. Or another way to say it is, if we have some small ions in a compound and they're going to be close together, such as somebody like a lithium chloride or lithium fluoride or something like that, they're going to be very difficult to melt and they're going to have a higher melting point. And that's all governed by Coulomb's law. And here's a good case in point here. So let's just take a look at this first four. We have sodium fluoride, sodium chloride, sodium bromide, sodium iodide. The only difference between these ionic compounds is our nonmetal. We have fluorine, chlorine, bromine, and iodine. And as you know, going down the periodic table, going down the halogen group with the fluorine, the chlorine, the bromine, the iodine, these guys are getting larger. Okay, so the distance between the nonmetal and the metal becomes greater and greater and greater and greater and greater. And like I said before, in that formula, E equals K Q1 Q2 over distance, or they had it listed as R. If you increase this value, you're going to decrease this value. And so look what happens as you go down this periodic group here. You're going from sodium fluoride, which has a 908 melting point, degrees Celsius, all the way down to sodium iodide, which is 686. So what we should be able to explain is, we should be able to explain as students, why is it that sodium fluoride has a greater melting point than sodium iodide? And the answer would be, well, sodium iodide has a greater distance between the two ions. Okay? Okay. And now one thing I should mention here is on our calcium oxide here, look at this melting point, 3,540 degrees Celsius, a really high melting point. And the reasoning for that? Well, the reasoning for that is going to be the charge differential in this formula. You have Ca with a 2 plus and oxygen with a 2 minus, and so you have a greater charge differential, and that is going to cause the lattice energy to go up. It's going to cause the melting point to go up drastically. So a great test question might be put in order, you know, maybe something like 3 different compounds, and maybe we did something like, you know, like what was up here, so lithium chloride, lithium bromide, and magnesium oxide. Put those in order from least to greatest melting point, and you should be able to do that. And we'll talk about tomorrow in class what the answer to that is. Okay, let's talk a little bit about metallic solids now. And when we're talking about metallic solids, we're talking about 2 different sort of categories. First off, we can have a pure metal like iron, or a pure metal like copper, and these are going to be just atoms of iron or just atoms of copper. And then we can also have an alloy. An alloy is a simple definition, is just a mix of metals. And so we'll talk more about that in a few minutes here. But let's talk about the general structure and what we're talking about here. So metals are good conductors of heat, as we know, and they're also good conductors of electricity. And good conductor of heat, of course, if you've ever grabbed a spoon that has been in a pot of boiling water for some time, you know that spoon's going to be really hot on the end, even though that wasn't in the water. It just transferred that heat right up there. They also conduct electricity because, you know, copper wire is often used, or gold wire is often used to conduct electricity. Now the reasoning behind this, and why is it so good of a heat conductor and an electricity conductor, is because of what we call a sea of free-floating valence electrons, and we call that metallic bonding. And so what is a sea of free-floating valence electrons, or metallic bonding? Well, here's a good little picture down here. And so what we have in this kind of, each one of these is we have a positive ion from a metal. So imagine this is our positive ion from our metal, and then, or our nucleus, and then we have electron clouds that don't necessarily belong to any one metal. So these electron clouds are all smushed together. So basically an electron could maybe belong to this nucleus, but then it could also float around over here somewhere, and maybe this electron is going to float around over here. And so there's constant movement, intermovement of these electrons, which allows an easy flow of heat and electricity, and that's what's going on with metals and metallic solids. We'll be talking more about that in class tomorrow too. A couple things here that we need to talk about. We got that picture down there of our USA gymnastic team. let's talk about why are they biting onto their gold metals. And metals are malleable and ductile, fun word to say. Now, what this means is malleable, they can be just hammered into a shape, or they can be pulled out into a wire and still retain a lot of this good, valuable characteristics, things like conducting heat and electricity. Now, we can also have metals that are alloys, and this is where we get into alloys. And an alloy is this: it's a material that contains more than one element in its characteristic properties of the metal. For example, an alloy. If you have 24 karat gold, that's considered pure gold. There's nothing but gold atoms in 24 karat gold. The problem with 24 karat gold is it's a very soft metal. So in the old days, you may have seen an old Western or something like that, or movie, where people will have a gold coin, and to verify that it's a gold coin, they'll bite it. And if they bite it, they can leave a tooth mark in the gold coin if it's 24 karat gold, because 24 karat gold is very, very soft metal. Rings that are made out of 24 karat gold would easily ding and leave a scratch or something like that. So that's why our gymnast team there is biting into it. It's kind of a kitschy little thing that people do when they win a gold medal, is to prove it's real. They'll all take a picture of themselves biting it. But it comes from that old way to tell if something's gold is you bite it and see if it leaves a tooth mark. Well, one of the things that can combat this soft metal and always having dings and teeth marks and gold things is you can make 14 karat gold. Now, 14 karat gold is an alloy. It's a mixture of gold, and it's also copper. They melt these two together, and this is going to increase the strength while still retaining some of the characteristics of gold, that nice shiny gold color, and the copper will add a little bit of orangish color to it as well. Okay. Now, let's talk about the two different types of alloys, and I can already see I made a typo there. This is 2. Substitutional alloys are two metallic compounds that have a similar atomic radii and chemical bonding characteristics. And now sometimes we do have substitutional alloys. Good one is we could melt gold with silver to make a new alloy because they have similar atomic radius. Interstitial alloys are the next one we'll talk about, and these are ones usually when we have a lot smaller non-metal that's bonded to the neighboring metals in a metal, and the presence of the bonding allows it to become a lot stronger and a lot harder of a metal. And here's a great example. The great example is steel. Steel is a mixture of iron, Fe, and carbon together. This is an interstitial alloy, and the amount of carbon put with the iron really determines the strength. High carbon steel has a certain percentage of carbon in the steel, and oftentimes they'll use this for cutlery or something like knives. They'll also use it for tools. They want something that's really going to, in the case of a knife, it's really going to hold that edge. It doesn't dull easily. So they'll change the carbon mixture in that. Down here is just a picture of what this kind of looks like. If you were given an image of it, a substitutional alloy would have, notice how our metals are listed in black, and then they've melted in some other metals to maybe give them some strength or whatever. But there's only a few of them here, and they have roughly the same atomic radius. Where an interstitial alloy here, there's going to be our metals. And then down here we've got these really small, in red, are probably nonmetals. They're not always nonmetals, but probably nonmetals that have been melted in there to give it some strength as well. We're going to stop there for tonight, so you get a short video, and we'll be talking more about alloys and metals and characteristics tomorrow in class.